Everyone watching knew the airplane was going to crash. What they did not expect was this fireball. There was nobody on board. The cockpit was empty. The cabin was filled with instrumented crash dummies, and the NASA test pilot was flying the jet from a control room on the ground. On December 1st, 1984, NASA and the Federal Aviation Administration deliberately sent a Boeing 720 into a row of steel cutters. The test had one urgent question. Could experimental fuel stop a survivable crash from turning into an unsurvivable fire? The answer arrived in seconds. It looked like a spectacular failure, but hidden inside this footage is the reason a failed test can still make flying safer. Ordinary jet fuel creates a dangerous second event after impact. When a wing tank tears open at speed, the fuel can break into a fine mist. Tiny droplets expose far more surface area to oxygen. So one hot engine part or electrical spark can ignite a moving cloud of fuel. Researchers mixed Jet A with a long-chain polymer called FM9. The modified fuel was known as anti-misting kerosene. In smaller tests, it resisted breaking into that easily ignited spray. There was a catch. The thickened fuel could not simply be fed into a turbine engine. Each of the Boeing's 4 engines needed a device called a degrader to break the polymer down again before combustion. The system was complicated, but the laboratory results looked promising enough to justify a full-scale answer. That answer took more than 4 years to prepare. NASA converted the airliner for remote control. Test pilot Fitz Fulton flew it from a ground cockpit using live video and telemetry. Before the final crash, crews completed 14 test flights, including 10 remote takeoffs, 13 remote landings, and 69 controlled approaches. The final flight lasted about 9 minutes. The tanks held roughly 76,000 pounds of modified fuel. The landing gear stayed retracted. 8 steel posts waited in the dry lake bed, positioned to slice open the wing tanks as the fuselage slid forward. The plan was precise. Touch down wings level on the center line and let the cutters release the fuel under controlled conditions. The fuselage was supposed to remain largely intact. Cameras, seats, restraints, recorders, windows, overhead bins, and hundreds of sensors would capture what happened next. But at the last moment, the jet was not level. The left wing hit first. The airplane rolled and yawed about 13 degrees away from the planned attitude. Instead of meeting the cutters straight on, it turned across them. One post struck the right inboard engine, ripped it apart, and opened a massive fuel path beside an ignition source. The fireball swallowed most of the airplane. The damaged right wing folded over, burning fuel entered the cabin, and the fire took more than an hour to extinguish. If the goal was a clean demonstration of fire-resistant fuel, the image looked devastating. The FAA did not require airlines to adopt the additive. Full-scale reality had exposed problems that small tests had not. Airflow, hydraulic fluid, damaged engines, and fuel leaving the wing in unexpected ways all mattered. The final impact was also more severe than the carefully planned, survivable crash, so researchers could not treat it as a perfect yes or no experiment. That nuance is important. The fuel concept failed to prove itself, but the test itself did not produce zero value. 97% of the sensors on the fuselage, wings, seats, dummies, and cabin systems were working at impact. Researchers collected more than 300 detailed histories of loads and acceleration during the first second. The cockpit floor briefly saw forces near 14 G. Much of the remaining cabin stayed at 7 G or less. The seats remained attached to the floor, while interior cameras showed panels falling and dummies being thrown against their restraints. That evidence helped engineers test crash models and gave the FAA real-world information about seats, fire prevention, fire-resistant cabin materials, windows, storage bins, and recorders. It was data that no small laboratory rig could fully reproduce. So why crash an entire passenger jet? Because a safety idea that only works under perfect conditions is not ready for passengers. The fireball did not give researchers the answer they wanted. It gave them the answer the full system produced. That is the hidden clue in this footage. The explosion is not proof that the experiment was pointless. It is proof that scale reveals interactions a laboratory can miss. Real footage, hidden mechanisms, fast answers. Subscribe for the next clue.